Hello, everyone. As everybody's walking in, please come on through. I'm about to give a presentation on gas and usage on pipelines. Hot topic. Hello, Joe. Feel free to take a seat. All right, so hello, everyone. I'm with Terra 15. Uh, Very nice to be here. Thank you for Microseismic for welcoming us to do this presentation. The topic of today's talk is liquid or gas, buried or exposed. Gas perfect for pipes. Indeed it is. Gas is in fact perfect for pipes, just about every kind. Quick intro on the company. Terra 15 has been around since roughly 2017. We're a highly technical, strong technical team full of engineers, physicists, small to medium-sized company currently. We have a very diverse technical and applications background, everything from geophysics to mechanical, electrical engineering. We manufacture our systems, we hold the patent on these systems, we develop them every day, and we support them completely vertically integrated. Today we have two principal products, the first being the Treble gas interrogators, Treble and Treble Plus. These are fantastic systems, and as you might see by the name, we're really trying to focus on the high frequencies of these systems. Now that is the perfect choice for pipeline applications. When leaks are produced, we're generally getting high frequency sounds. When there's third-party interference, construction activity, people trying to tap into the pipes, these are in fact also high frequency sounds. Lastly, we offer end solutions. These end solutions include pipeline monitoring. We digest all the data that these machines can produce, and you can imagine a 40-kilometer, on average, one of these machines can measure up to 40 kilometers. That produces tons and tons of data, terabytes per day, in fact. We digest that data autonomously through a series of algorithms, and we produce an output for our customers that is effectively a stoplight system. Green is good, yellow is something that's slightly wrong, maybe really wrong, and red is we now have a serious problem. There's probably a leak happening. Let's talk about distributed acoustic sensing very, very briefly and the way that this works and why this is special and why it's so good for pipes. So what I'm showing here is a little diagram, very schematic and very conceptual. You can think of the interrogator as having an optic system built into it, a series of lasers, photodetectors, amplifiers, everything you would find in a telecommunications array. Within it is also quite a lot of compute, so it's a high-end computer at the same time. And what we do is we send a pulse of light down the fiber. That first pulse captures a fingerprint of every location along that fiber. There are imperfections in the fiber itself. First pulse gives you these imperfections, tells you exactly what the writing is, that's your fingerprint. Subsequent pulses track a change in the fiber. Now, if you have some sort of disturbance in the fiber at a given position, that produces a vibration that changes that fingerprint ever so slightly. If you interrogate this fast enough, you can actually see exactly what's happening in that position. Disturbance, and it lights up. Right? And fundamentally, here what we're talking about is sending light down the fiber and seeing the reflections. These imperfections generate a reflection, comes back to the interrogator, and we can read that. Slight technical. All right. In this demonstration that I'm going to show here, whoa. Apologies. Right. What I'm showing here is 16 kilometers of fiber deployed in the city of Perth. So up here are interrogated. This is 0 meters, so right at the start of the fiber. And we work our way down through the city, down out to this bridge in the bottom here. Now, I want to note that this fiber is standard telecommunications fiber, about 2 to 3 feet below the ground, thin conduit, not purposed for anything other than telecommunications. We just placed a single core and started sensing. Now, how do we tie this together? So I mentioned 0 meters at the top, that's 0 meters at this position along the x-axis, and we're out roughly to 15 kilometers here at the end of the fiber. So we'll cut off just about here. There's a number of features, and principally what we want to start looking at are the vibrations felt along the fiber. The way you read that is the dark purple, dark blues, that's the low vibration intensity. The light colors, the yellows, the greens, that's high vibration intensity. So we're seeing some cars traveling up and down the road. That's in fact these diagonal lines. There's some stationary features. So we might have a pointer. You cannot see on the television. So there's some stationary features being shown here. There's also some really intense yellow features there. That's actually a train as it moves alongside the road. And you'll see it as it comes up again, but that's our train here. Once it deviates away from the fiber path, we stop seeing it, roughly about 100 to 200 meters away from the fiber path. Now I'm going to play a couple of sounds. This system, as I mentioned, is extremely sensitive at high frequencies. It allows us to play back acoustics. And I'm going to play some of those back, and I'll just point out what that looks like visually, where we're extracting those sounds. Alright, so I've maxed out the TV there, so perhaps not all the sound will come through. But that's a jackhammer, and that jackhammer is being seen at one position in time. And it's just high vibration intensity at that one position. It's intermittent. That could be one of these locations here. So that's a pothole that I've just played. The car's driving along. For example, in this position here, this car would have been driving and got to that position. Bang, bang, bang. That's the front and rear axle going over that pothole. One more. So again, another stationary position. That's a construction site. We just tune into that position and we play the audio back. That would have been the train coming into the station. And as this replays, you'll see that in a little bit more clarity, and I pointed out. But this is the train coming down its track, stops at the station, picks up its passengers, moves to the next location, stops, picks up its passengers, so on and so forth. Now, I can hardly hear that one, so I'll just talk over it very briefly. That's the sound of bubbling. It's a drainage that's blocked. It's not flowing very well, and that can actually be heard. That has implications for infrastructure monitoring as well. What it sounds like when somebody plays with fiber. And if you guys want to hear that, I can do it on the interrogator that's sitting right next to you there, and you can see when somebody messes with the fiber, what that sounds like. Now in terms of higher frequencies, that one's just excellent. Sirens produce an enormous amount of high frequencies, high amplitude, high frequencies. Right, liquid and gas pipelines, varied, exposed, various materials, HDPE, plastics, steel, cement. When these pressurized pipes leak, they produce a signal, they produce a sound, it's vibration. Traditionally, this is the way that we use to detect leaks, especially in city centers. Man goes out there with a listening stick, puts his ear on the pipe, yep, I hear a leak, and then determine where exactly that is. At scale, it looks like this. That is not scale. That's not scalable at all. So that was analog. Let's enter the digital age. The digital age, we have DAS. And what I'm going to play here, this is some early work that we did back in Perth. And we had one of our engineers go out and they generated a leak on one of these fire hydrants. For reference, our fiber path is about 3 meters, 2 to 3 meters from the hydrant. As the hydrant is opened and closed, vibrations are either actuated or turned off or stopped. So we'll see it again. Vibrations on from the leak. Signal response starts to occur. We know the exact position along the fiber. Nobody needs to go out there and stick their ear on the ground. We know where that is. Where can we use it? Well, you can use it on the processing end, transport end, storage end, equipment, rotating equipment, fans, conveyor belts, pipelines, other infrastructure, and also seismic use cases, great many seismic use cases. mentioned it's good for any pipe. Excellent versatile pipeline monitoring technology. If it's buried in a specific conduit, great, no worries, just drop the fiber in there. On the surface, water, multiple materials, slurries, just as good if it's pressurized, we can listen. Subsea, processing plants, hydrogen, you name it, it's good. If it's pressurized, it's good. Where do we place fiber for these different deployments? Well, really you have a great many options. You can either place it directly on the pipe at the time of burial or at the time of deployment, or you can put it next to the pipe. There are trade-offs for each one. There are specific situations where you wouldn't use one or you would use another. But in general terms, if you drop a fiber alongside your path, a buried pipeline, you pretty much instrumented that for the next 30 to 40 years. Well worth it. Standing's a bit off here, so just talk through it. Hydrogen and CCS, whether it's production, transport, or storage, this is very near and dear to our hearts, and we're working quite hard already in this space. There are hundreds of large-scale hydrogen and CCS projects proposed every year. Thousands of kilometers of these pipelines and thousands of tons of materials per year. Recent estimates are putting this upwards of $206 billion projected in annual revenue growth. This is an enormous market. This is a massive market, and it requires monitoring. The failure of any one of these, whether it's hydrogen or CCS, is completely unacceptable. It's either an enormous loss of money because hydrogen is incredibly expensive to produce, or a loss of containment for something that we're trying to contain desperately, carbon sequestration. We do work in this space already, and we're creating strategic partnerships to better capture these markets. So if you guys want to have this conversation in more detail, approach us or approach Microseismic. We are working together in partnership. This is going to be the future, especially in North America, and we're really looking forward to working with you. Please come talk to us. And I think that's it. Any questions? Thank you.